Welcome back. So, in the last class, we have started our discussion on dual active bridge. So, as we have seen this configuration, it has two bridges, one on the primary side and one on the secondary side. And we have discussed it will be using 8 fully controlled devices, may it be IGBT or MOSFET, based on the power rating and the application. We can have an external inductor, or we can use the leakage inductance of the transformer for this L, which will be responsible for the power transfer, which we will be seeing today in details. Then for analyzing this circuit, first we have assumed that the secondary side of the transformer terminals were short circuited. Then we have assumed that the output stage is short circuited. Now we will continue the discussion from there. And first, in this case where the output bridge was circuited, we have considered the delta to be 0. Okay. So, what is our delta? It denotes the phase shift between the voltage generated by the primary side and the voltage generated by the secondary side, or I can say the delay between the two bridges. So, when delta was 0, we have observed that the power transfer was 0. Why? So, if we see the area of I2, it is equal and opposite. So, the amount of charge which is dumped in first quarter cycle, that will be removed in the other quarter cycle. Okay, so these are exactly equal and opposite. So, they will cancel out each other and net power transfer is 0. Then we have seen the case where our delta was equal to 45. Okay. So, what is the meaning of this 45? If I mark this S1 and S4 as my reference gate signals, the same corresponding switches on the secondary side, if I see, they are delayed by 1 division or 45 degrees. Okay. Or if I see the voltage which will be generated by these two bridges, I will see that they will be delayed by 45 degrees. As of now, we have assumed V2 to be 0. So, when we go into the actual operation, we will see this. Okay. So, what is the meaning of delta and how the voltages will be having the same shift as corresponding to the delta. So, in this case, what was the power being transferred? If you see this yellow portion which is negative, it will be getting cancelled out with this small portion and will be left with the 4 divisions. Okay. So, 4 divisions, 2 plus 2 minus, they will be cancelling out each other. The remaining 4 divisions will be participating in the power transfer, and we will have a net positive power transfer, that is the power will flow from V1 to V2 if we have some load at the output terminals. Then delta equal to 90, further we have shifted the pulses by one more division, that is it is delayed by 2 divisions now. So, it is delta is equal to 90. In this case also we have found out what will be the I2 waveform. So, we have seen that it is always positive. So, all the divisions are now participating in the power transfer. If I calculate the power which will be transferred from V1 to V2, in this case it will be maximum. Why? There is no negative part. So, there will be no cancelling out of the current terms while calculating its average value. So, maximum power will be transferred in this case. Okay. So, now moving ahead from this point, here we have assumed the delta to be 135, that is we have further delayed the pulses by 45 more degrees. Okay. So, here if you see the starting of our S1 and S4 and the S5 and S8, so they are having 3 divisions delay. So, from this division to this division, so 45 into 3, that is 135. In this case, again as we have not changed anything from the primary side, so we will try to find out what will be the I2 waveform. So, I2 waveform from our conclusion, that is I2 will be same as IL if my positive switches, that is S5 and S8 are on. So, if you see for these 4 divisions where my S5 and S8 are on, so it was positive, so it is maintained positive, it is positive, it is positive. So, here also it is positive, so it is maintained positive. Here it was negative, so it becomes negative. Okay. Because S5 and S8 are on, so they will always follow the IL curve. Okay. So, I2 will be same as that of IL. Now, for the remaining 4 divisions where S6 and S7 are on, they will have a opposite polarity as that of my IL waveform. Okay. So, here if you see IL is negative, so it becomes positive. So, in this division it is negative, so it becomes positive. So, here it was positive, it becomes negative. So, in the last division here also if I see it is S6 and S7 are on, so here it was negative, so it becomes positive. So, from our conclusions we have found out that this will be my I2 waveform when the pulses are delayed by 135 degree or delta is considered to 135 degree. Now, in this case what will be the power being transferred? If this is my I2 waveform, what will be the power being transferred? So, let us go back to the 45 degree case. So, in this 45 degrees case, if you remember, the 4 divisions were cancelling out each other, and which divisions were participating in the power transfer? It was these 4 divisions which are marked in tick mark. So, if you see, they are adjacent to the peak value of the current. This is my I max value. So, this is my peak value. So, this is also my peak value. Okay. So, if you see, the divisions which are adjacent to the peak values are participating in the power transfer. Okay. So, now let us go back to our 135 degrees. In this 135 degrees, we have observed the current waveform to be in this way. Okay, so from our conclusion, the same can be calculated by using the dot conventions of the transformer. Now, here if we see which are participating in the power transfer, this will cancel out with this one, this will cancel out with this division. Okay, so again we are left with the divisions which are adjacent to our peak value. Okay, so from this intuitive analysis, can I say that the delta equal to 135 and delta equal to 45 both have the same power transfer? Yes, if you see, so the 4 divisions which are corresponding to the peak value are participating in the power transfer. So, from this simplified analysis we can conclude that the power being transferred at delta equal to 135 and 45 will be one and the same. Okay. So, and it is positive. Why it is positive? If you see, the positive current durations are left out and other parts are getting cancelled out. So, net power will be transferred from V1 to V2 when my delta is equal to 135. Now, let us consider delta to be 180 degree. Okay. So, if you see, exactly we have shifted the pulses by 4 divisions. Okay. So, in this case when I shift it by 4 divisions, what will be the effect on my I2 waveform? So, here S5 and S8 are on for these 4 divisions. Okay. So, when the S5 and S8 are on, so what will be the relation between IL and I2? I2 will be following my IL waveform. Okay. So, if you see here, so it was positive, positive, then for the last 2 division it is negative. So, the same has been repeated over here. Okay. So, whenever S5 and S8 is on, my IL will be having the same polarity as that of I2. Okay. Now, the other case, other 4 divisions where my S6 and S7 are on, I know that the I2 waveform will be exactly opposite of IL. So, here it was negative for this 2 division, so it becomes positive. Then after that it was positive, so it becomes negative. Okay. So, from the dot convention also we can find out the same thing. Okay. So, let us consider this as an example. From the dots we will find it out. So, over here if you see, the current is positive. Okay. So, in the 4th division, and which switches are on the secondary side? It is S6 and S7. Okay. So, we have S6 and S7 in the on condition and my current is positive. So, it is entering the dot. So, it will try to leave the dot on this side. Okay. So, what will be the path for that? It will flow through this and back. Okay. So, if I see now what has happened, so it has flown through this and this way. Okay. So, if you see, it is negative. Okay. So, because it is in the opposite direction of our measurement, so the same thing which we have found out from our conclusions. Okay. So, whether it is from the dot or from our conclusions, we will always see that when S5 and S8 are on, I2 and IL will have the same polarity, they will follow each other. When the opposite case is true, they will have reversal in the polarity. Okay. So, now let us come back to the power being transferred in this case. Okay. So, when delta equal to 120, if I see, again we have gone back to the case 0 where we had equal positive and negative areas. Okay. So, if you see the yellow area over here, the area which is highlighted in yellow color and the area which is highlighted in green color, they are exactly equal and opposite. So, they will cancel out each other and there will be no power transfer between V1 and V2 even if we have some load or battery over here. Okay. So, there will be no power transfer when delta is equal to 180. Okay. Now, let us see when delta equal to 225. Okay. So, when delta is equal to 225, how it is so? If you see over here, this was our negative to positive transition of S1 S4, which we have marked as our 0 axis or the start of the cycle. Okay. So, from this point where my S5 and S8 has the similar transition, if you see we have the similar transition over here. Okay. So, this is the complementary transition, that is it is becoming 1 to 0, but here in this case it becomes 0 to 1. So, we want to see the rising edge. So, this rising edge is over here. So, if I count the delay, so it is 5 division delay. So, 5 into 45. So, it will be 225 degrees of delay in the pulses between the primary and secondary side bridge. So, now for this case what will be the I2 waveform. Okay. So, first we will go from the conclusions. S5 and S8 are on for these 4 divisions marked over here. So, whichever is my IL waveform, the same will be followed over here. Okay. So, here the IL is negative. So, it is negative. So, here it is positive. So, it will be positive, and here in these 2 divisions it is negative. So, the same is maintained over here. Okay. Now, let us see when S6 and S7 are on. Okay. So, when S6 and S7 are on, my I2 and IL will have opposite polarity to each other. Okay. So, for this division, if you see the current was negative, so it becomes positive. So, for these 3 divisions it is positive, so it becomes negative. Okay. So, 3 of the divisions where the current was positive, now the output current has become negative, and for this first division where my IL was negative, it gets flipped and it becomes positive. Okay. So, this will be my load current when I have delta is equal to 225 degrees. Okay. So, let us consider one division and find it out from the dot conventions. Okay. So, here if you see the last division where the IL is negative. So, what is the meaning of that? It is flowing in this direction or outward of the dot. So, on the secondary side it will try to enter the dot. So, how it will flow and which devices are on in this case? It is S5 and S8. Okay. So, it will try to flow in this way and complete the path. Okay. So, here if you see this I2 and the actual current flow are opposite to each other. This is our direction of measurement, but the current is flowing in the opposite way. So, the I2 waveform is negative. Okay. So, whether from our conclusions or from the dot conventions, we will always see that the currents IL and I2 will be having the same polarity when my S5 and S8 are on. They will be having opposite polarity when S6 and S7 are on. Now, let us see what is the power being transferred in this case. Okay. So, when my delta is equal to 225. So, let us see which areas will cancel out each other. So, now this area will cancel with this one, this area will cancel with this one. Okay. So, these 4 areas will be cancelling out each other. Now, which will be left for us for the power transfer? These 4 divisions. Okay. So, which we can mark over here, these 4 divisions. Okay. Suppose I see where these 4 divisions are located, they are around the negative peak current. Okay. So, if you see this is the current has become negative, 0 is over here. So, now here the average is negative for sure. Why? Because net negative area is left with us, these 4 small areas. Okay. So, let us mark it again. So, here we have this and this 4 divisions participating in the power transfer, because the other ones will be cancelling out each other, and these 4 divisions if you see the current is negative. So, net power is negative. Okay. So, that is what is written over here. What is the meaning of power being negative? Now, in this case if I have some battery bank over here or an active load over here. So, what will happen? Now, after this cycle I will observe that net power is being transferred from the output stage, that is from the V2 side to the V1 side. Now, power has become reverse. Okay. So, if I connect a battery bank over here, it will get discharged. Okay. So, why this discharging mode is important for us? We have one more operation, that is vehicle to grid operation. When we go into the chargers, we will see that what is V2G and G2V. There we will see the bidirectional power flow and their requirement. Okay. So, in this case what is happening? The power flow is becoming negative. Okay. So, intuitively what will be the value of the power? If I take delta equal to 45 or 135 as my base case, Okay. So, in this case we have already discussed the power was positive and they were equal. Okay. So, in 225 the power transferred will also be equal, but it will be in the opposite polarity. Okay. So, what is the meaning of that? So, which divisions are participating in the power transfer? Here again the divisions which are adjacent to your negative peak current are participating in the power transfer. If I find the area analytically also, I will come to the same conclusion that the power transferred at these three angles, that is 45, 135 and 225 will be magnitude will be the same, but the polarity will be opposite. That is, it will be positive for 45 and 135 and it will be negative with the same magnitude for 225 degrees. Okay. So, we will not see the further delays. Okay. So, the next delay will be at 270. Okay. So, what will happen at 270? Again the complementary case for our delta equal to 90, where the current will always be negative and maximum power will be transferred from V2 to V1. Okay. So, the power will be maximum when delta is 270, it will be equal to the power being transferred at 90. The magnitude will be equal, but the directions will be opposite. At 90 maximum power is transferred from V1 to V2, at 270 it will be transferred from V2 to V1. Okay. The same power will be again be transferred when I go for next 45 degrees, that is 315. So, these 4 angles, that is 45, 135, 225 and 315, they all will have the same magnitude of power transfer. Only thing is for 45 and 135 it will be positive, for 225 and 315 it will be negative. Okay. So, till now we are just seeing the simplified version of our DAB, because we are assuming the output stage to be short circuited in this case. Okay. Now, let us see some conclusions before going into the actual operation of our DAB. Okay. So, what we have observed, when delta was between 0 to 180 degree, power was positive, that is it was flowing from V1 side to the V2 side, or from the primary of the transformer to the second side of the transformer. It was maximum positive when delta was 90. Maximum power will be transferred at 270 also in the opposite direction. And when my delta becomes greater than 180, the power flow direction is changed, that is from V2 to V1 side the power will be flowing. So, when I control the delta value between 0 to 180, I see the power is flowing in one direction. When it is between 180 to 360 degree, the power will be flowing in the other directions. If I want maximum positive direction of power, I will set it to be 90 degrees. The delta value will be set to 90 degrees, and if I want maximum negative power, that is maximum power in the reverse direction, I will set it to 270 degree. I can say that as minus 90 as well. Okay. So, this is what is the simplified DAB circuit. Okay. So, we have two controlled voltage sources over here, AC sources over here, which are generating square waves. Okay. They are separated by the inductance. Okay. May it be the leakage inductance of the transformer or an external inductor. Okay. So, we have an inductor and we have two sources on either side. Now, the power flow will be controlled by controlling the delta value. Okay. So, this power flow will now depend on L value. Okay. But once the circuit is designed, the L becomes fixed. Okay. So, during design stage I can manipulate the L value to control the power flow. Okay. But once I design the circuit, L will become fixed. So, how I will control the power flow? By changing the delta value. Okay. Or by changing the position, relative position between these two voltages, primary and secondary side. That is what we are doing by changing the delta value. Okay. By changing the relative position of the voltages, we will be able to control the power flow in both the directions. Here in this case, when we were discussing about the transformer equivalent circuit, we have seen that it has many components. Okay. Here we are neglecting the magnetizing inductance and we are assuming it to be open circuited, so that there is no current flowing through the parallel branch. We are only considering the series component, that is leakage inductance. Okay. So, why we are doing so? Because the operation of frequency of operation of this converter is assumed to be very high. So, the magnetizing inductance we are neglecting it and considering it to be open circuited. Okay. So, this is done for our simple analysis, or else the analysis will become very complicated. Okay. Now, the input and output side we of the high frequency transformer are high frequency square waves shifted by an angle of delta. Okay. So, if I see the transformer terminal which voltage is being superimposed on it, it is experiencing the voltage which is generated by the two active bridges. Okay. So, one bridge is present on the primary side and other bridge is present on the secondary side. They will be generating a square wave voltage which will be shifted by delta based on the power flow requirement. Okay. So, from 0 to 180 the power is in one direction, from 180 to 260 the power flow is in the opposite direction. So, after my DAB is designed, I will control the delta value to control the amount and direction of power which will be shared by the DAB. Okay. So, now till this discussion we were assuming the DAB to be having short at some of the terminals. Now, we will relax that assumption, we will go to the actual loading condition of the DAB. Okay. So, we will consider that as an example we have an charger which is having an input DC voltage of 400 volt and it is producing an output voltage of 800 volts. Okay. So, if the input is 400 and the output is 800 volts, so my N will be 2. Okay. So, we are assuming 1 is to 2. So, 400 is on the primary side and 800 on the secondary side. So, the transformer turns will be 1 is to 2. Now, what has been asked to us, first to sketch the inductor current, then to find the load current if single phase shift control technique is used. Okay. So, what is this single phase shift control technique? The control technique which we were discussing till now falls in the name of single phase shift control technique. Okay. So, there are many ways of operating the DAB. The simplest way is to consider the bridge to be operated at 50% duty ratio and with complementary operations. Okay. So, that is S1 and S4 we are considering as getting the same pulses, S2 and S3 are considered complementary to S1 and S4. Okay. So, in this case I did the simplest mode of operating the DAB where we will have one control variable, that is delta. Okay. So, this method is called a single phase shift control technique. We will see a brief discussion on what are the other control techniques and what is the merits and demerits of each one of them. Okay. So, when I say single phase shift control technique, so the one which we have discussed, that should come into the mind. Okay. So, here now we want to find out the inductor current and the load current value. So, here we will assume and delta to be equal to 45 degrees. Okay. So, let us assume that we have this loading condition 400 at the input stage, 800 at the output stage, n is equal to 2 and my delta is considered to be 45. Okay. So, as an example. Now, as given in this question, the input is 400 and the output is 800. So, why the plus minus is written over here? Now, the voltage whether it is positive or negative, it depends on which switch is on in the bridge. Okay. So, on the primary side we have one bridge. If S1 and S4 are on, then we will get plus 400. When S2 and S3 are on, we will get minus 400 volts. Okay. So, plus 400 volts will be applied when S1 and S4 are on, and if the complementary switches are on, we will get minus 400. Same way on the output stage we also have one bridge. Okay. So, based on which two devices are on, we will get plus or minus 800 volts. Okay. So, this denotes all combinations of voltage which can be applied across the transformer and inductor terminals. Okay. Now, let us consider the primary bridge first. Okay. So, in the primary bridge, as I said, we are considering an example of single phase shift control technique. So, S1 and S4 will be on for 50% of the time and S2 and S3 will be on for 50% of the time, because in single phase shift control technique we assume 50% duty ratio. Okay. So, now what will be VAB? In this case, when S1 and S4 are on, when this switch and this switch is on, so what will be the voltage VAB? So, where is A now? We will consider this node as A, this node as B in the circuit. Now, we will find out what will be VAB voltage. When S1 and S4 is on for these 4 divisions, it will be equal to plus V1. How? Because A point is connected over here, B point is connected over here. If I see apply KVL in this loop, I will observe that the voltage across the terminal A and B will be equal to V plus V1. Okay. So, in this way I can apply KVL in this loop. Okay. And I will observe that VAB will be equal to V1 when S1 and S4 is on. Now let us see the next 4 divisions, okay, where S2 and S3 are on. If S2 and S3 are on, now the VAB voltage will be equal to minus V1, okay, so which is 400 in this case, okay. So if S2 and S3 is on, this node is connected to the negative bus, this node is connected to the positive bus, okay. So if I now apply KVL to find out the VAB voltage, I will observe that it has become negative, okay. So when S1 and S4 are on, it will be applied with plus 400, when S2 and S3 are on, it will be applied with minus 400 volts. Now, so this 400 is when S1 and S4 are on, this minus 400 is when my S2 and S3 are on. Now, as we are assuming delta to be 45, so this is our actual loading condition now. We have both V1 and V2, where V1 is 400 in this example. In this example, we are considering V2 to be 800 and N is considered to be 2, okay. So, how we have got this 2? Because we want 400 volt to be becoming equal to 800. So, we will have, if we have 1 turn in the primary side, we will have 2 turns on the secondary side and so on, okay. So, because and V1 by N1 equal to V2 by N2, okay. So, that should be maintained. So, here in this case, if you see this case, when S1 and S4 are on, we can have S6 and S7 on the output stage, okay. So, in this case, what will be the secondary side voltage, or these two, the voltage between these two nodes, it will be equal to minus 800, okay. So, when this equivalent circuit is true, when S5 and S8 are on, what will be my Vs? It will be equal to plus 800, okay. So, here in this case plus 800, minus 800, here plus 800, minus 800, okay. So, because of this presence of your primary and secondary side bridges and their operations, as they are having some finite value of delta, we will get all the 4 combinations, okay. So, we have also seen when we have delta is equal to 0, we will get only 2 combinations of the equivalent circuits, okay. Now, let us see this operation for the first division, okay. So, in this first division, if we see which switches are on the primary side, it is S1 and S4, okay. S1 and S4 are on. On the secondary side, S6 and S7 are on, okay. So, S6 and S7 are on, and on the primary side S1 and S4 are on. If I apply KVL on the primary side, I will observe that VAB will be equal to plus 400. When I apply KVL on the output stage, I will observe that Vs has become equal to minus 800, okay, because this node is connected to the negative bus, this node is connected to the positive bus. So, we get minus 800, and on the input side we get plus 400, okay. So, now what is our next case, okay. So, in our next case, if you observe for the next 3 divisions, there is no switching operation, okay. So, we have one switching after the first division, that is S5 and S8 are turning on the secondary side bridge, whereas on the primary side the still S1 and S4 are maintained with the same pulses, okay. So, S1 and S4 are on the primary side, there is no change on the primary side. So, plus 400 will be as it is. Now, on the secondary side we have switched on the complementary devices, that is S5 and S8 are on. So, now this terminal is getting connected to the positive bus, this terminal is connected to the negative bus. So, we will get plus 800 at the output voltage, okay, or the secondary side voltage will be plus 800, Vs is equal to 800, okay. So, this is true for the next 3 divisions or from the division 2, 3 and 4. After that, in the 5th division, we will again have one more switching operation, okay. So, what is done on the primary side, we had switch the 2 and 3 devices, and 1 and 4 were switched off, okay. So, we are turning off 1 and 4 and we are turning on S2 and S3. So, in this case, if I apply KVL in the input side, I will observe that VAB will become equal to minus 400, okay. But on the secondary side, still the same pulses, that is S5 and S8 are on. So, it will be plus 800, okay. So, what we are doing till now? We are first we have fixed the pulses on the primary and secondary side. We have eliminated the primary bridge first, then we have eliminated the secondary side bridge. Now, we will find out what value of voltage will be reflected across the inductor terminals by eliminating the transformer. Okay. So, we are going step by step, so that the circuit becomes simple for us to understand. Okay. So, here in this case what has happened, now we have remove the pulse from S5 and S8 and we have provided the pulse to S6 and S7. Okay. So, if here S6 and S7 are on, so in this case this terminal is connected to this point, this terminal is connected to the positive bus. So, we will get minus 800 on the input side, it is minus 400, and on the secondary side or the output side it is minus 800. Okay. So, in this way we have found out what will be the voltage on the primary and secondary side after eliminating the bridges. Okay. Now, this VAB, why we have assumed VAB, why not the VP on the primary side? Because we have inductor in series. Okay. So, the voltages will be different. Now, these are the 4 equivalent circuits by eliminating here primary and secondary side bridge. Okay. So, what we have done till now? First we have assumed the gate pulses, then first we have eliminated the primary side bridge, then we have eliminated the secondary side bridge. Now, we have got this simplified circuit from the DAB. Now, we will simplify it further by eliminating the transformer. Okay. So, here in this for our analysis we have considered the leakage inductance to be present on the primary side. It is not a mandatory requirement, it can be present on the secondary side. Based on that, for eliminating we have to map the voltage which is present on the opposite side of the transformer to the other side. Okay. So, here when 800 volt is applied over here, if I want to eliminate the transformer and I see what will be the VP voltage, for this case it has to be divided by 2. Why? Here we have 800 volts and the turns ratio is given as 1:2. So, whichever voltage is present on the secondary side, 50% of that will be reflected on the primary side. Okay. So, now if I eliminate the transformer for the case 1. Okay. So, where this case 1 was valid for this first division. Okay. So, which is marked over here. For this first division, if I eliminate the transformer, I will see that this was minus 800. What is the meaning of that? This dot has become negative. Okay. So, here it is Vp is equal to minus 800 and by 2. So, that will become minus 400. Okay. So, on one side we have plus 400, on the other side we have minus 400 across the inductor. Okay. So, in today's class what we have seen? We have seen the operation of DAB with our simplified analysis, that is by considering the output state to be short circuit, we have changed the delta value and we have found out what will be the relation between delta and the power being transferred. Power is transferred in the positive direction or from the input to the output stage from V1 to V2 when delta is between 0 to 180. When it is between 180 to 360, it is in the opposite direction, and power transport is maximum positive when delta is equal to 90. Power transport is maximum negative when it is delta is equal to 270 degree. Then we have tried to understand the actual operation of DAB by considering an example. We have seen that the inductor current will be having this shape. Okay. So, it is trapezoidal shape, and how we have got this, that also we have seen. So, we will continue from this point in the next class. Thank you.